check 79.
I did great. Which is 85. Is that 85? What? I did much better.
Alright. To solve a right triangle. Crazy. To solve a right triangle means to find the measure of all the angles and all the sides. In order to do that, all you need are 3 pieces of information. 3 combination of angles and side lengths. Okay? If you have those, then you can find the rest of the triangle. Okay? If you're not given a sketch is really, really important to kind of help keep everything organized. When we're looking at our standard nomenclature of sides A, B, and C and angles A, B, and C, angles are represented with uppercase letters. Side lengths are represented with lowercase letters. Side A is opposite angle A. So you see side A is opposite angle A. And side B is opposite angle B. Side C is opposite angle C. And C is reserved for our hypotenuse and our right angle. Okay? A and B can be whatever as long as they're opposite each other. Side C is reserved for our hypotenuse and angle C is reserved for our right angle. Okay, so that's some of the standard nomenclature for our right triangles. So to solve, we use a combination of Pythagorean theorem as well as our trigonometric ratios. Okay, you're going to need your calculator to do this. And most importantly, you need to make sure that your calculator is in degree mode. When you reset your calculator, it defaults to radian. So you need to make sure that you are in degree mode. Otherwise, you will get completely different answers. Okay? You need to make sure you're in degree mode. All right? So when we're solving our right triangle, we look at the information that we have. We decide what side we want to solve for first, or what piece of information we want to solve. And we're going to use our sine, our cosine, or our tangent. Okay? We're going to use either sine, cosine, or tangent. When I'm using sine, what 2 sides are involved?
Opposite and hypotenuse.
Opposite and hypotenuse. When we're using cosine, what 2 sides are involved?
Adjacent and hypotenuse.
Good. And then our tangent. Flip that.
Opposite over adjacent.
Okay? So we look at what side we know, and we have to determine, okay, well, my hypotenuse is the side that I'm given, and so I have to make sure I'm using a trig ratio that includes the hypotenuse. I have to know one part of that ratio. So I have to use either sine or cosine, and I'll actually use sine and cosine both to find the other 2 sides. Okay? I can't use tangent because I don't know the opposite or the adjacent side. I have to use sine and I have to use cosine. Okay? And so we're going to look at the angle measure that we have. Okay? We have angle A. So sine of angle A is equal to the opposite over the hypotenuse. Well, what side is opposite angle A?
A.
Side A, right? So the sine of A is going to be equal to A over our hypotenuse. We have to know 2 of these 3 values in order to solve. Well, I know angle A is 34 degrees and 30 minutes. And I know that side C is 12.7 inches. So we can plug those in to our equation. 34 degrees and 30 minutes, sine of that angle measure will equal the length of side A divided by the length of side C, which is 12.7. Algebraically, what would we do to isolate A and solve for it?
U times the 12.7. Both sides.
We'll multiply both sides by 12.7. So that cancels, leaving me with A all by itself, and then our calculator just takes over from there. Again, making sure we're in degrees mode. We're going to have 12.7 times sine of 34 We need to put in our degrees since we've got degrees in minutes. If you don't have degrees, minutes, seconds, you don't have to put in the degrees. You could just type 34. But since we have degrees, minutes, seconds, we do have to differentiate between the degrees and minutes. Okay, so we can just take 12.7 times sine of 34 degrees and 30 minutes and get our solution. And A is going to be approximately 7 point. And what we're going to do is we're going to use significant digits, and it looks like we only have one, so we're going to round it to the first decimal place. Okay, you're going to want to pay attention to the rounding. Usually, I just tell you where to round. Say 1 decimal place, 2 decimal. So side length A is approximately 7.2. Okay. So if I want to solve for side B, what ratio am I going to use? If I want to solve for B, what ratio am I going to use? I use sine to solve for A, cosine, because that's my adjacent side, right? B is adjacent to angle A. So cosine of A will equal B over C. And so we plug in just like we did before, which is 34 degrees, 30 minutes equals B over 12.7. Okay? And then we want to multiply both sides by 12.7. The benefit of this is this equation is almost identical to this one. What's the only difference? Cosine instead of sine. And so we can actually do some copy paste. We can go up, select that, and go back to sine, and just change it to cosine. And look how fast that was. A little bit of copy paste, like so much easier. And so we get the value of B. We get the value of B to be approximately 10.5. Okay, and then lastly, we need to solve for our missing angle. All right, we have all three of our sides, we need all three of our angles. We know two of them, the 90 degree and the 34, 30 minutes. What can we do to solve for angle B?
You can change the 34, 30 into the other form in your calculator, and then add that up with.
I mean, we don't have to do that first part. Because if we have degrees, minutes, seconds, we're going to want to leave it in degrees, minutes, seconds. But we can just, we want to go ahead and subtract it using the triangle equality. Remember, angle A and angle B always have to add up to 90. So you don't need to include the 180. You can if you want, but we can just do 90 minus our angle, 34 degrees and 30 minutes. So we've got our decimal. If you're given degrees in degrees, minutes, seconds, you want to make sure you rewrite it back in degrees, minutes, seconds. So you can just do a quick conversion to DMS and you've got 55 degrees and 30 minutes. Because it was given in DMS. If it's not given in DMS, then it doesn't need to be in DMS. But if it's given in DMS, it needs to stay in DMS. Okay? That's how we solve a right triangle. Now, there's some variations on the solution and the order that you can do it. Okay? We could have solved for angle B right at the beginning and used angle B for everything. Right? Or we could have done sine of A and sine of B in order to solve for side A and side B. There's some variation, okay? But I want to offer this warning, okay? Most of the values we solve for, or I guess 2 of the 3 that we solved for, were rounded values. They were estimates, okay? When at all possible, don't ever use an estimate to solve for another thing. Because most of the time it might be okay, but it's not always going to be exactly the same. Your rounding could affect your values. So if I tried to use cosine of B with my side A, which was rounded, my side length B could be changed from that, and I could be off by literally 0.1, but it's still wrong. You don't want to use rounded values in any of your future calculations, so you want to make sure you are as precise as possible. So when you can, use only the values given in the problem to solve for everything else. That's not always possible, and sometimes we have to be really careful with our precision, but when at all possible, use the values given, exact values, to solve for any of the missing information. Okay, and that's what this is basically saying. Okay, you want to make sure that you use the information that's provided, and if at all possible, avoid rounding early. Okay, if you're using your calculator and you're doing this, the 12.7 times cosine of everything, if you're doing it all at once, you don't have to worry about that. But if you're finding cosine of 34 degrees in 30 minutes, and you get that value, and then you round it, and then you multiply it by 12.7, you're going to lose some precision in your answer, and you might be off by 0.1, 0.2, 0.01. Okay, you might be off by just a little bit, but it's enough to get the question wrong. So you want to make sure that you maintain as much precision as possible, and avoid rounding any intermediate steps. Okay, so here we've got another triangle to solve. So we've given two side lengths. What can I do to find the third side length? Yep, we'll use our good old-fashioned Pythagorean theorem. So we have, that's a highlighter. We've got a squared plus b squared equals c squared. So again, paying attention to what side is what. Again, c is always reserved for the hypotenuse, whether they give us a diagram or not. They don't have to give us this picture, and we still need to know that those two sides, C is our hypotenuse. It is reserved for that in this instance. 29.43 plus b squared equals, that should be squared, 53.58 squared. So we can take 53.58 squared and minus our 29.43 squared, and that's going to give us our b squared. Okay, I don't want to round this yet because I'm not done. I don't want to round it early. We're going to want to round to 2 decimal places at the end to be consistent with our significant digits, but we don't want to round it too early. And we can go ahead and take the square root of our answer, and then we'll go ahead and round to our significant digits. So 44.77 for the approximate measure of side B. We will not use side B in any other calculations. We will only use side A and side C because this is rounded. We want to leave it alone and never touch it again. We're only going to use A and C. All right, let's start alphabetically with angle A. We want to solve for angle A. So given that we're not allowed to use B because it's a rounded value, we have to use side A and side C. What trig ratio can I use that includes side A and side C? Sine, opposite, and hypotenuse. Opposite angle A and our hypotenuse. So sine of A will equal 29.43 over 53.58. Okay? Now, to get A by itself and to find the angle measure, the inverse of a trig function is legitimately just called the inverse trig function. The inverse of sine is called inverse sine. And so to find the measure of angle A, we will take the inverse, that's what that little means, that little -1, the inverse sine of our ratio, and that will give me the measure of the angle. In degrees, because our calculator is in degrees mode. Our calculator is in radians mode, it would give us the measure of the angle in radians, which is really weird for a triangle. We don't ever want to do that. Okay? And so right above our sine, our cosine, and tangent on our calculator, you see in the blue text, sine to the -1, cosine to the -1, tangent to the -1. Those are our inverse functions. We use those when we want to find the measure of the angle. If we don't know the measure of the angle, we'll use our inverse sine with the ratio 29.43 divided by 53.58. And then we get the approximate measure of our angle, 33 point, let's do 2 decimals, 32. Okay, so there's a measure of angle A. It is approximately 33.32. Now we could be a little more loosey-goosey with the angles because the rounding has to kind of add up to 180, but we're going to practice using our trig ratios again. So let's look at angle B. Okay, given that I have to use side A and side C, what ratio can I use to find angle B? Cosine, because we have to use our adjacent and our hypotenuse. Okay, so we will use cosine of B will equal the adjacent side divided by our hypotenuse side. And then again, we'll do the same thing with our inverse trig functions. So the inverse cosine of the ratio. And again, because we've done this, we can actually, again, do some copy-paste. The ratio hasn't changed. Okay, the ratio is still the same. So I can copy what I did before and just change inverse sine into inverse cosine. And that'll allow me to get my angle measure of approximately 56.68. And now we've got all three sides and all three angles. Yes?
Could you just do like...
Yeah, with the angles we can be a little more loosey-goosey because we know it has to add the 180 the rounding. But I wanted to practice the angle or the trig function. Go for it. What do you guys think? We just don't want to use that 44.77 with everything. All right. So now we're going to take this triangle information and we are going to move into some application with what we call angles of elevation and angles of depression. Okay. Angle of elevation and angle of depression measure the difference in the angle from a horizontal line of sight. Okay, a horizontal line of sight. Angle of elevation is how far we're rotating up from a horizontal, while angle of depression is how far we're measuring down from a horizontal. Okay? What's really, really important is they are always measured from a horizontal. If you can remember that, the word problems get really, really easy. Forget that, then you're probably going to get like half the word problems wrong. You need to remember that your angle of elevation and your angle of depression are always attached to a horizontal line. Okay? So, look at that. Always horizontal. Alright, so you have this general step when we're applying our trigonometry problems. Draw a sketch. Does not have to be a Picasso level painting. Okay? I don't expect any Rembrandt or Monet's. But draw a diagram. Usually it's going to look like a triangle with maybe something else to kind of indicate what the sides and the angles represent. Okay? But you're going to want to sketch. Label the quantity that you need to find with the variable, and then label any other information that you're given. Using that sketch, you can write an equation using whatever appropriate trigonometric function, sine or cosine or tangent. Okay? Then we'll solve the equation and make sure our answer makes sense. Okay? So we're going to start with Shelley standing 123 feet from the base of a flagpole with an angle of elevation to the top of the flagpole at 26 degrees and 40 minutes. If her eyes are 5.3 above the ground, we want to find the height of the flagpole. Okay? So we're going to draw a little sketch. We have Shelley. She's a little person right here. Okay? There's Shelley. Say hi, Shelley. Thank you. All right? There's Shelley. And Shelley loves flags. She's a flag aficionado. And so she often spends her days staring at flags.
Oh,
Because she's weird. But you know what? She's living her best. So she's staring at this flag. All right. And so we have two things. We have Shelly's line of sight on a horizontal line. Okay. We also have the flag that Shelly's looking at. The horizontal line of sight and the flag that she's looking at form a triangle, which is why it's a trigonometric application. Okay? So what we want to do is we want to find how tall the flagpole is. Okay? I want to find how tall the flagpole is. Well, if we have a triangle right here, here to here to here, okay, we're going to be solving for this side length here. All right, we're going to be solving for that side length of the triangle, that vertical side. However, that isn't the entire height of the flagpole. What part are we missing? The bottom part. How long is the bottom part? How tall is the bottom part? 5.3 feet. How do we know that? That's where her eyes are. Her eyes are 5.3 feet off the ground. So below that horizontal, that distance is 5.3 feet. So that's the leftover. So we need to consider that. When we solve for x, we need to remember to include that additional 5.3 feet that's not included in that vertical measurement. Okay? So Shelly stands 123 feet away from the base of the flagpole. Well, here's the base of the flagpole, and here's where she's standing. That's 123 feet, which means that the base of our triangle is 123 feet. Her eyes will be the same distance from the flagpole as her feet will be from the base of the flagpole. So that part is going to be 123 feet. Last thing we need to fill in is our angle of elevation. Okay? Well, we know that this horizontal line and this vertical line make a right angle, and so we have to figure out, well, is that going to be this angle here or this angle up here? And if we remember that our angle of elevation and our angle of depression are always attached to a horizontal line, it means it has to be from her line of sight. Always attached to a horizontal line. Always, always, always. So we know that angle is going to be 26 degrees and 40 minutes. All right? So given that I want to solve for side x and I know the base of the triangle, what ratio are we going to use? Sine uses what two sides?
Opposite and hypotenuse.
Do we know the hypotenuse?
No.
Cosine uses what two sides? We have our opposite side and we have our adjacent side. So we have to use our tangent. Tangent of our angle will equal the opposite side over the adjacent side. Just like when we were solving our triangle in the beginning, we'll isolate the variable, so we'll multiply both sides by 123. And then we plug in and solve. 3 times tangent of 26 degrees and minutes. And so we get x is approximately 61.8. I'm making a judgment call. I'm right around there, 61.8. Okay. All right, so what is the total height of our flagpole going to be? We need to remember to add the 5.3 from her height to get our 67. Total height. By nature of these problems, tangent gets used a lot. Not for all of them. It will not always be tangent, but tangent does get used a lot because rarely do we have something that gives us the hypotenuse. Usually we're measuring horizontal distance and vertical distances. But there will be a few where we'll use sine or cosine. We want to find the length of the shadow of a building that's 34.09 meters tall. The length of the shadow of a building that's 34.909 meters tall is 34.62 meters. We want to find the angle of elevation to the sun. So we have a building. Look at this beautiful building. Here's Shelly looking for flags. There she does. Okay. There's our building. And we have a shadow cast by the sun. Okay. Sun's casting a shadow for our building. We know our building is 34.09 meters tall, and our shadow is 37.62 meters long. We want to find the angle of elevation to the sun. Okay? If we take those two sides and we finish our triangle, is angle of elevation going to be the angle at the top or the angle at the bottom?
Angle at the bottom.
Angle at the bottom. Has to be attached to the horizontal. It's always drawn for the horizontal line. So we want to solve for that angle measurement. Given that we want to solve for angle x and we have the two sides shown, what trig function are we going to use? Okay, don't tangent the line. If we're using the horizontal and the vertical, we're using tangent. Right? Tangent of x equals 34.09 over 37.62. And what do we use when we want to find the measure of the angle given the side lengths?
The opposite.
Inverse tangent. So we use our inverse tangent. 34.09 over 37.62. Say that again.
42.1.
Is she right? Cool, sweet. Oh, we don't have to type it. So approximately 42.18 degrees is our angle of elevation of the sun. Are we good, or we need another? You good? All right. So, angle depression of a buoy from the top of the Barnegat Bay Lighthouse is 130 feet above the surface of the water, 6 degrees. Find the distance x from the base of the lighthouse to the buoy. So we've got water and the lighthouse. There's a little light. Okay, and in the water, off in the distance, we've got a little buoy. Okay, little buoy. So the angle depression of a buoy from the top of the lighthouse. That means if we're looking at from the top of the lighthouse down to the buoy, okay, the angle of depression, that means from the horizontal point of view, that angle of depression is 6 degrees. Okay. So we kind of actually have more of an inverted triangle here, but I'm going to show you a little trick that might make it a little bit easier. Okay. So we've got our angle of depression, and we know that the lighthouse is 130 feet above the surface of the water. So we have this vertical distance here, 130 feet. Okay. 130 feet above the surface of the water. We want to find how far the buoy is from the base of the lighthouse. So this distance here, how far is the buoy from the base of the lighthouse? Okay. So we have that angle of depression, right? But it's not really inside this triangle that we see here. But it doesn't really have to be. Okay? Because angle of elevation and angle of depression are always attached to a horizontal line. If we look at these two horizontals as being parallel lines, here and here, with our hypotenuse being a transversal, we have here and here alternate interior angles. What do we know about alternate interior angles? They're the same. So, if my angle of depression from the lighthouse is 6 degrees, the angle of elevation to the lighthouse also has to be 6 degrees. They will have the same value. So when you draw your triangles, as long as you remember that your angle of elevation and your angle of depression have to be attached to the horizontal line. It's really hard to screw up the triangle. Given that we've got our angle and the two sides given, what ratio we're going to use? Use tangent again. Okay. This one will be a little bit different to solve just because of what side we have. Tangent of 6 equals 130 over x. What are we going to do to solve for x? We're not going to divide by 130 because the problem is that x is in the denominator. How do I get x out? Multiply by x first. Divide by what? So we're going to divide both sides by tangent of 6. So then we're left with x equals 130 divided by tangent of 6. So we get that the buoy is approximately 1,236 point. No, so we'll do the whole distance. 1, 2, 3, 7 feet away. Or meters or whatever it is. I think we have one more, right? Far and wide for one that didn't use tangent. You good? Alright. We have a guy wire connects the top of an antenna to a point on level ground 5 feet from the base of the antenna. Alright, so here's an antenna. Alright, so a guy wire, you know those big giant steel cables that you see attached to like power lines and stuff? Those are called guy wires, okay? Those are there just to kind of help keep it stable in the high winds. So from the top of the antenna down to the ground, we've got a guy wire, alright? It is 5 feet from the ground. My drawing is not to scale. Okay, it's 5 feet from the base of the antenna is where it attaches. The angle of elevation formed by this guy wire is 80 degrees. Angle of elevation is on the horizontal, 80 degrees. We want to find the length of the wire and the height of the antenna. So we're solving for two things. The length of the wire, I'll do L, and H for the height of the antenna. You can use whatever variables you want. Just make sure you remember which one's which. We want to find the length of the wire. Let's do that one first. Given this angle, this side, and I want to find the length of the wire, which function are we going to use? Because we have the adjacent side. That's our right angle. Our guy wire is our hypotenuse. So we will use cosine of 80 equals 5 over our length. Okay? Just like with our last one with tangent, because we have that variable in the denominator, we'll multiply first by the variable. Oopsies. That one. So we have length times cosine of 80 equals 5, and then divide cosine of 80. Okay? So 5 divided by cosine of 80. We get a guy wire that is approximately 28.8 feet long. What ratio are we going to use to find height? We can't use the hypotenuse for anything because that's a rounded value. We don't want to use it for any future computation. So we still need to use this one, which means we're going to have to use tangent of 80 equals 5. So we actually get a value that's pretty close, 28.4 feet long. So the guy wire and the tower are approximately the same length. They're off by just a little bit. So draw your pictures, label them very carefully. Make sure your angles of elevation and angles of depression are attached to the horizontal line of the triangle. Horizontal line. Okay. Questions, comments, concerns, queries? Well,